Welcome to a new weekend project. Now, this is truly a weekend project. I don't think you would be able to build it to perfection in just a couple of hours. Well, maybe you can if you're really handy. But let me tell you, this is a circuit which takes a little bit more tweaking and handiness than, just cobbling together a few parts. Okay, enough mystery. I'll tell you what it is. So, you know that I like to build simple circuits and preferably, if possible, cheap circuits because personally I don't have that much money to spend on my hobby, and also I'm busy with restoring old radios and all that, and it seemed kind of fitting that I would at least try to understand a little bit more about the subject of high frequency. Now, mind you, I'm not an engineer in high frequency equipment or anything, so just like many of you, I have to learn by reading about it and trying to understand it, of course, and then building it. Now, the thing is, there's quite a bit of theory that has been written about high frequency stuff, and a lot of it is, reasonably complicated. But since I'm not a professor and I'm not an engineer, I'm going to try to explain to you in simple terms, at least the way I interpreted what I learned, to you. So I'm not going to use, if possible, very complicated words and all that. And I'm also going to simplify a few things. If you want more information or more complete information, well, I'd advise you to start on Wikipedia, and from there on move on to perhaps more complete information somewhere else on the internet or from books. Now, okay, like I said, enough mystery. What have I been building? Well, if you are involved like me into restoring old radios and old TVs, you will certainly be familiar with the concept of IF alignment. Now, as you all know, IF alignment is about aligning or tuning, if you want, the internal circuitry of the reception part of a radio or a TV. And it's kind of an infamous subject because, like most of you will agree, IF circuitry can be tricky to repair and to align in the end. Aligning meaning that you make the intermediary frequency circuitry work to perfection so that reception on your radio or TV is perfect. At least I'm talking about analog radio and TV, okay? I'm not talking about digital stuff here. So I thought, well, what would be a simple or relatively simple thing to build that would teach me a little bit about IF stuff and radio frequency stuff and all that. And Well, it didn't take me too long to find something that would be interesting to build, and more precisely what I built, and which you see here, this part of the circuitry. So forget about this stuff, this is something different for another weekend project. But this stuff here, this part here, where you see the two blue capacitors, is in fact a radio frequency generator, and more precisely a oscillator, if you wish, because you know radio frequency is generated with oscillators. It is a high frequency oscillator, and to be even more accurate, it is what people call a Colpitts oscillator. Now, I'm going to get to the theoretical bit in a second, but the basic thing is that it is, if you look at it, a reasonably simple circuit. It's built around one transistor, and you see the transistor over there, this one here, and this transistor here, this transistor here is a BC547, or to be more generic, it's an NPN transistor, okay? And according to its specifications, it's capable of handling up to frequencies up to 100 megahertz. It's very cheap, it's dirt cheap. I love using BC547s. They are cheap, they are reliable, and you can use them for DC circuitry, or in this case high frequency circuitry, and they work like a charm. Okay, one BC547 I think you can get for as little as 10 cents a piece, or even less if you buy them in large quantities. I bought my BC547s in a quantity of, I think, 100 pieces, and it cost me less than $5. So there you go. Then there are a few capacitors in the circuitry. You know, there are two 330 picofarad capacitors, which you see here. Then there is a mica capacitor, which is this one here, which is 150 picofarad. And then you have a regular sort of ceramic capacitor of 10 nanofarads, this one here. And you have a few resistors. Now, the whole circuitry, I think, and you have a very important part, which is this green one here. I don't know if you can see it, but let me zoom in a little bit so you have a better view. Okay, so this part here, this one here, is a coil, and coils are a lot of times are expressed, the value of coils is Henry. Okay, you will hear millihenry and microhenry, but really the unit for impedance is Henry. Okay, just remember that, it's enough. Okay, so the circuitry, as you see here, is built up of readily available parts on the marketplace. I don't think the circuit costs more than, say, $5 all in all. Okay, I admit, if you have to buy a few tens or even a few hundreds of these parts, it'll cost you more, of course. But if you calculate it part by part, the price is about $5, which is really cheap. Okay, it has a little potentiometer over there, but a potentiometer like that costs perhaps 30 cents. So really, it's dirt cheap. Okay, so that's positive. But what is not so positive, unfortunately, is the complexity degree of it. So that's why I'm saying that if you're going to build something similar, you're going to need a weekend. Okay, so or at least say 4 or 5 hours to get it right. Right, okay, so what did I build actually? Well, what I built actually is a high frequency RF generator. And as you well know, if you have to align a radio or TV, you need to produce a base frequency, which most of the time in most radios, for example, and I'm talking about AM radios here, is 455 kilohertz. Now, honestly, I didn't want to pin myself down on 455 kilohertz. I mean, only on 455 kilohertz. I wanted something which could generate also 450 kilohertz and 452 kilohertz, 455 and even 457 kilohertz. So that's why there is that little potentiometer over there. But we'll get to it in a moment. So what I basically built over here is the high frequency part of an RF generator. A little bit like my heat kit, which is over there. Yeah? So that is a ready-made high frequency generator, okay, which is fully tunable to thousands and thousands of frequencies. I mean, it's an analog RF generator, so you can basically generate anything between 100 kilohertz and 100 megahertz, okay. But I wanted to keep this circuitry simple because I wanted to learn something about high frequency stuff, and well, like I said, I wanted to keep it cheap and simple. Also, a lot of you will know that generating a high frequency is really not the only thing you need. Since I'm building this to align specifically AM or amplitude modulation radios, you also need to modulate the high frequency signal. Now, to modulate a high frequency signal in amplitude, so because that's what AM means, amplitude modulation, you need to superimpose a low frequency signal over the high frequency signal. Yeah, so you have to, as it were, modulate the amplitude of the high frequency signal. Amplitude, if you remember, is in fact the height of the sine wave. Okay, so the height of the sine wave is the amplitude, and I do the modulation of the high frequency signal with another oscillator, which is this one here. Now, this one, as you can see, is also built around two very cheap, very reliable BC547s. So there's one here and there's one over there. This is really dirt cheap. I mean, you can build something like that for under $1 if you're lucky. The most expensive parts really are not the transistors, but the electrolytics. Okay, there are two 1 microfarad, I think 25 volts, 1 microfarad electrolytic capacitors. So, and these are more expensive than the transistors, imagine that. So yeah, a few resistors, 2 capacitors, and 2 transistors, and that's it. It generates a very low frequency, I think 170 Hertz, which is a very low sound, you know, woo. And the reason why I picked a low frequency is because the 300 Hertz that is generated usually for IF alignment, or sometimes it goes even up to 400 or even 1 kilohertz, really gets on my nerves. It's if you have to listen to it, it's so high pitched that after a while it really starts to get to me. So I said, okay, I'm going to build an oscillator which generates a more agreeable frequency to me, which is around about 170 Hertz. Okay, well, there's not much to say about this. This is what is called an astable multivibrator circuit. So in effect, it generates a square wave signal, albeit when we will look when we will watch the signal on my oscilloscope, you'll see that it's not really a perfect square wave signal, but it's fine for the purpose for which I'm going to use it. Okay, so you need a low frequency generator and a high frequency generator. Now, it's imperative, in my opinion, that the high frequency generator produces a very nice, clean sine wave signal. Why is that? Well, because if you start messing around with high frequency square wave or perhaps triangular wave oscillators, because you are, if you use those, you are also creating a lot of what people call harmonics. Okay, there are certain cases where harmonics are desirable, but in our case it is not desirable. Okay, so and sine wave generators have a lot less tendency to generate all sorts of noise and unwanted frequencies and all that. It still generates harmonics, by the way, but they are easier to filter out. So you can really get a very pure signal, and that is exactly what we want. Now, okay, why did I settle on building a so-called Colpitts generator? Well, one more remark. As you can see, I built the whole circuitry on a breadboard. Now, honestly, if you're going to build high frequency stuff, and I mean in the kilohertz range, it's still reasonably feasible, but once you go up into the megahertz and certainly in the gigahertz range, this kind of breadboard breadboard won't do. Forget about it. It really is not accurate enough, and it creates all sorts of noise and other signals and all that. So this kind of setup is good for, say, or up to a couple of megahertz, if you're lucky up to 10 megahertz, but that is really about the limit of it. Because as you can see, I'm using also little bridge wires and all that. And if you are building a high frequency circuit, well, one of the first things you should do is keep all your parts as close together as possible to the active component, which in this case is the transistor. You should also keep all the leads as short as possible, and that includes also the wires. Why? Well, since you're working with high frequency, all these little leads, you know, the leads of the parts and these little connection wires, are really all of these are little antennas. And as you know, an antenna is perfect in picking up all sorts of high frequency signals. And even low frequency signals. So if you're going to build something really accurate which creates high frequency signals, you should really do it with very short leads and on a print board which is electrically shielded. Okay, but we'll get to all that in a second. Okay, now a little bit of theory. The Colpitts generator, which we'll be building, is, or which I have built, is built around, like I said, a transistor you see here, and a few components around the transistor. It's, as you can see, it's a very simple circuit. There are, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, and ignore for the moment these two parts. So I would say 9 parts for the basic Colpitts generator. And you can even don't look at this capacitor yet. I'll come to it in a moment. Okay, so the basic circuitry is really this part here, in black, without this one. Okay, so the Colpitts oscillator, as far as I understand, is basically built around what people call a tank circuit. Now, a tank circuit, if you look that up on the internet, on Wikipedia or any other source, and even on my page you'll find a video which explains tank circuits. A tank circuit is built basically around a capacitor and a coil. Okay, so you have the capacitors here and you have the coil. Now, I'm not going to bore you with all the theory about oscillations and all that. Basically, you can find all that information explained in Wikipedia and other websites far better than I could ever do. But basically what you have to remember from all the theory and all that is that the capacitor and the coil, if you bind them together, if you connect them together, they form a circuit which will create a sine wave current. Okay, so if you would measure the current at any end of that circuitry and you pump some electricity into it, then you know the capacitor will charge up and then discharge itself back again into the coil. But as you know, a coil, when you pump current through it, it will first try to resist that. So the voltage will slowly rise, and then once all the energy of the capacitor is in the coil, then the coil will generate a current in opposite direction and will drop again. So you will get basically a sine wave when the capacitor charges up. Then it pulls current away from the spool or the coil. When the capacitor discharges itself into the spool, then the spool will try to counteract that. And that interaction between capacitor and spool creates the sine wave. Okay, so that's in a few words what a tank circuit does. You have all sorts of setups, you know, but basically what you have to remember is that unfortunately most parts are not ideal. Okay, in an ideal world you could create an oscillator with just a spool and a capacitor and an energy source like a battery or something like that, and that's it basically. So, but since the parts are not ideal, in other words, since they do also have a little bit of resistance and they also leak a little bit of voltage and all that, you need basically something which compensates, if you wish, the losses that occur in a tank circuit, so in a capacitor coil setup. And that is basically what the transistor does. The transistor pumps in at the right moment just enough current into the LC circuitry, yeah, to keep it going, yeah. And it does that at the right rhythm, you could say, at the right frequency, yeah. So you could compare it like a seesaw, or when you sit on a seesaw and it's perfectly balanced. If you push once, you will go up and down a few times, but then because of friction the movement will ultimately stop. So you will oscillate a few times up and down, but due to friction you will stop. Now if you push yourself away from the ground exactly at the right moment, you can keep the movement, the up and down movement, going. And that's basically what the transistor does. The resistance in this case is not friction, but resistance in the coil and the capacitor assembly in the tank circuit. And the resistor gives just enough voltage and current to the tank circuit to keep it going, to keep it oscillating. Now, the basic circuitry is this capacitor here and this coil here. Now, this capacitor you see between the emitter, which is this, since it's an NPN transistor, the emitter is the arrow here, yeah, and it goes away from the base of the transistor. Okay, so you have the collector, which is this part of the transistor, and you have the emitter. And between both there is a small capacitance, or a small capacitor. Now that capacitor gives feedback, which means that it will allow the circuit to start oscillating. Yeah, so you need, just like a seesaw, if you want to start it going it to go up and down, you need at least the very first time to give a push, an initial push. And the feedback capacitor does just that. Now, mind you, this is my interpretation, okay? If you don't agree, or if you want more accurate information, go look it up. But this is how I understand the circuitry. Now, the transistor you see here is connected to the LC circuitry, or the tank circuit, through this resistor to its base. Since the transistor is an NPN transistor, it is basically, you could say, driven by positive voltage. But as we all know, an NPN sine wave has not only a positive part but also a negative part. If you want the transistor to keep conducting as well for the positive part of the sine wave as the negative part of the sine wave, you need to bias the transistor. And that's exactly what these two resistors here do. Yeah, this is just a load for the transistor, but and it also has an effect, of course, on this capacitor, but it's minimal. It's really to provide a load for the transistor. Yeah, because the coil has very little resistance, and the capacitor has very little resistance. If you don't provide a load to the transistor, it might overheat. So this is basically a load for the transistor. These two resistors provide enough bias on the transistor's base so that it keeps conducting over the full range of the sine wave. Okay, so the positive and negative part of the sine wave. So in effect, what you do is you push the voltage level of the base up from the normal ground voltage, which is 0 volts. Okay, if you would put the base directly to ground, it wouldn't conduct at all. Yeah, or maybe a little bit. If the high frequency signal goes into the positive part of the sine wave, then it might conduct. But basically you would get a notched signal like this. Okay, so that's we don't want. So what do? Well, we pre-energize the base so that it's not at ground voltage, so 0 volts, but a little bit higher, just high enough in fact, so that it can take the full wave frequency. Okay, now so the transistor, actually you can see a little bit like an amplifier, or if you wish, a kind of a switch. Yeah, it runs at high frequency, and it gives its function is really to give the little nudge, the little push, just enough push to keep the tank circuit oscillating. Okay, so it compensates really for the losses in resistance, in heat, if you wish. Yeah. So that's what it does. Now, you see a few parts which I haven't mentioned at all. The first one is this. Yeah, this capacitor here. Now, in a regular Colpitts oscillator, as far as I read about it, in a standard Colpitts oscillator you won't find this capacitor. However, if you read a little bit more about it, they say that if you add this capacitor here in parallel with this coil, you can actually tune the circuitry. So you can actually, you sort of filter out the frequency that you actually want. Okay, so by adding this capacitor, you limit the range of frequencies that goes out of the circuitry. So you make it more accurate if you wish. In my case, that turned out to be a capacitor of 150 picofarads. Now, I added myself this little circuitry here. Now, what that does is to change the bias on the base of the transistor. Basically, what I'm doing is I'm changing more or less the amplification it provides. Okay, so by augmenting or diminishing the resistance of the potentiometer, yeah, so by making the base either a little bit more negative or a little bit less negative, I can influence its amplification. And by doing that, I can also influence, but in a very narrow range, the frequency that it amplifies, yeah, and therefore it also changes a little bit the frequency that this Colpitts oscillator produces. Now, it has a slightly annoying side effect that it also reduces a little bit the maximum amplitude the circuitry can output. Okay, so it's not ideal, but it does allow me to change easily and with a minimum of parts the output frequency of the oscillator. So by using this little gizmo here that I built around it, I can change the frequency, say, anywhere between 404 kilohertz, which is its base frequency, and I think it can go up to, I didn't measure actually the maximum frequency I could get out of it, but I think it goes all the way up to about 470 kilohertz, which is really nice. So I can change the output frequency just by changing the value of the potentiometer. Of course, taking into account that I also change the maximum amplitude it can output a little bit. Not a lot, but it changes by, say, a few tens of millivolts, or even up to a few hundred millivolts. But that's really not too important, actually. So yeah, there you go. Now, if you're going to calculate the frequency the Colpitts oscillator can output, there is of course a formula. I mean, you can go about it doing it experimentally by using all kinds of parts until you find the right parts to do it. Yeah, but you can help yourself along a little bit by using this formula here. Now, it looks complicated, but really it isn't. And if you have a good pocket calculator, or if you use the calculator on your PC, well, it's really nothing. It's really easy to do. You have to remember one thing though. As you can see, to calculate the output frequency of the Colpitts oscillator, you need to take into account the capacitance of these two capacitors here and the impedance of the coil here. Now, remember, if you want to calculate the frequency, you have to use it with the values of these components expressed in units. So the unit of impedance is Henry, the unit of capacitor is Farad. So basically what that means is, if for example the capacitors here, one capacitor is 330 picofarads. So if you express that, so 330 picofarad, if you express that in farad, is 0.00000000033. Yeah. So I'm sure you forgot how many zeros I mentioned. Actually, I mentioned 9 zeros after the decimal point. So as you can see, if you input these values in this formula, you will be confronted with a lot of zeros. But if you do that, and if you calculate diligently this formula, you will get the base frequency at which a basic Colpitts oscillator functions. Okay, so without this capacitor and without these parts. So if you calculate this, you get the base frequency the Colpitts generator outputs. But okay, I used standard parts, and I tried to get as close as possible to the standard values that I had on hand. Now I used in my formula, I input the value of the coil I used, yeah, and which turns out to be 470 microhenry, yeah, not milli, microhenry, and so I used that in my formula. Now I did change a little bit the layout of the formula so that I could find in the end the value of the capacitors. I knew the frequency that I wanted, or at least that I wanted to approach, and I also knew the value of my coil. So I started playing around a little bit with the different values and all that, and it turned out that to get to around about 400 kilohertz, or a little bit above that, if I use 330 picofarad capacitors and a coil of 470 microhenries, I was somewhere in the ballpark. And then I used this capacitor to, as it were, pump up the frequency a little bit more, and to filter out what I didn't want. That, I'll admit, I did a little bit experimentally. I had an idea after reading all sorts of stuff over this type of oscillator that a capacitance, say anywhere between 100 and 300 picofarad, would work. So I just took a sort of an average value. I said, okay, probably 150 picofarads will do, and indeed it did. Okay, so you could say for that part I was lucky. I didn't calculate it, I just tried it out. I took resistance low enough so that it would pull the base of the resistor low enough so that it would still conduct, but on the limit of conduction, really. So then I added a potentiometer in series with it, so that I could change really the bias of the transistor. Okay, so that's all about the Colpitts. Now, I'm sure some of you will not entirely agree with my explanation, but I'm sure if you are diligent, you can go onto the internet and read all about it. So what I explained is really my interpretation of it. Okay, so about the other part, the sound generator, really, I can be really short. As you see, it's what people call an astable multivibrator. Okay, hang on. Oh, darn it. Come on. Okay, so the astable multivibrator, again, I'm not going to go into all the details about it, but what it does really is it produces a square wave output, and it's really simple. Yeah, it's built around a capacitor and a few resistors on both sides. Yeah, and the capacitor on one end charges up, and then when it's charged, it starts to make the other transistor conduct, which shuts down the other transistor and loads this capacitor, which in turn then makes this transistor conduct, which blocks the other transistor, and so forth and so forth. So, and it produces a square wave. If you want to calculate the frequency of the astable multivibrator, you use another formula, which is this one here. Yep. And if you use exactly the same values for your resistors and for your capacitors, you can even use a very simple formula, which is here. But I used asymmetric values, so I had to use this formula here. But with a good calculator and so forth, you can calculate the frequency, the base frequency of your multivibrator quite easily. Okay, so now let's have a little demonstration of the circuitry. Let me show you what it produces once it starts to work. Okay, so here is my power supply, and as you can see, I set it at 9 volts. Well, it can vary by a few tens of millivolts, but really I try to really make it run at 9 volts. Okay, so it outputs 9 volts into my circuitry here. Okay, so over there we have my oscilloscope, and it is set at high frequency. As you can see, we're in the kilohertz range. Okay, so let's see what it produces. Okay, so this white wire here outputs the high frequency signal. So I'm going to attach the probe. I don't know if you can see both. Okay, hang on, I'm going to switch off the light. Okay, you see the oscilloscope over there. So here we go. Yeah, well, that's what I'm saying. If you work with a breadboard, you always have a little bit of a bad contact. Ah, there you go. Okay, so as you can see, my RF generator, which is attached with a probe to the circuitry, at least if I can make it focus. Yeah, so you see it's attached via the probe to my oscilloscope. Well, as you can see, the frequency is 455 kilohertz. Okay, so you see here my cursors. Okay, so if I align them precisely, if I align my cursors precisely between the peaks, so you see, by varying the position of this cursor, I can read the frequency that is being output. So let me put it to the peak of the second one like this. Yeah, I think I'm close to, yep, there you go. So my circuitry outputs 455 kilohertz. Okay, now to show you that I can make the frequency vary, not a lot but still enough, I'm going to show you what happens when I change the value of this potentiometer here. Okay, so if we watch the screen, okay, see, yeah, okay, and just oops, yeah, it's a little bit twitchy because well, this breadboard is not ideal. Okay, so here we go. I'm going to change the frequency a little bit. Remember, it is very twitchy, the circuit. Oop. Okay, so I changed the frequency a little bit. Yeah. And if we put the cursors exactly to the top, there you go. So I changed the frequency to 431 kilohertz. Okay, so I can basically go all the way from the base frequency. So if I change the value of the potentiometer even more, there you go. Well, this is the base frequency, 404. And as you can see, what I said before happens. The amplitude of the signal, so the height of the signal, drops. So I'm at 5 volts per division scale. So if you look at it, you see that it's, I would say, 7 volts in amplitude. Okay, so it's 7 volts amplitude. If I raise the frequency, which I'll do right now. Need a little bit more light. Okay, let's go. Okay, so I raised the frequency, and now if we shift this to the divisions, and I supposed to set my cursors correctly. Okay, so I rose the frequency of my generator to 445 kilohertz. Okay, so yeah. Okay, so as you can see, the amplitude of my signal is way much higher. Okay, so where's my pointer? I put it away. Okay, so as you can see, the amplitude of my signal is now, we're still at the 5 volts setting here, the volts per division setting. So now we have 1, 2 and a bit. Yeah, say 2.5, which would make it 12.5 volts output. Yeah. Now, the reason why it is a bit higher than the voltage that I input into the circuitry, well, because I put it on 9 volts, okay, and it's outputting peak to peak 12.5 volts, not 9 volts. The reason for that, I believe, is strictly the amplification of the transistor at work. Okay, so that's it. The transistor amplifies the signal. Yeah. Okay, there's one last thing I need to show you. I'm going to show you the output of my multivibrator, so the low frequency part of the circuitry. Okay, here we go. So as you can see, this yellow wire here goes to the output of my multivibrator. Okay, here we go. Okay, the signal line disappeared, but we're still in the kilohertz range, so let's go down. There you go. So, this is the output of my multivibrator. Now, let's see. It's a little bit lower. It's not very stable, I have to admit. I've noticed that it's quite temperature dependent. Yeah, I'm using cheap parts, and one of the results of that is that if the transistors and the capacitors and the resistors all change in temperature, it does either raise or drop the frequency at which the multivibrator works, unfortunately. But well, it's not too important. I can work that out so that it becomes a little bit more reliable. But yeah, well, that's a problem, of course. But as you can see, it outputs a, well, it's not exactly square, but it's close to being square signal. Now I'm going to show you finally what it does. So that's the signal from the multivibrator. Now I'm going to show you what happens if we modulate the high frequency signal with the low frequency signal. Okay, so I attach. So in effect, I'm going to show you what happens when you modulate a high frequency signal in amplitude. Okay, so it's hooked up to the high frequency circuitry again. So let me raise this. Yeah, you see, the signal is not very clean here in this range. Why is that? Well, again, and it's quite twitchy also. Okay, it's back again. So the reason why the signal is really not very clean, as you can see here, this ripple here. Let me show you. Maybe you can see it better. Well, you can see there's quite a bit of ripple on the signal. Yeah, and the reason for that is what I said at the beginning. If you build a high frequency circuit like this on a breadboard, with all sorts of long leads for the parts and all sorts of connection wires and all that, you automatically pick up a lot of stray signals, so noise in effect, and that creates the noise on the signal you see over there. So now what happens when I modulate the signal with a low frequency signal? Well, let's have a look. There you go. You see? Now the amplitude is modulated. So in effect you can see the high end of the modulated wave and the low end. And in between you see sort of a dirty green band. Well, that's the low frequency modulation I put on it. So in effect, if you would inject the signal into a IF circuitry of a radio, you would get a very low woo sound. Okay? And there you go, without modulation. Well, I would say this concludes this weekend project, namely the building of a simple radio frequency IF alignment generator. I hope you enjoyed it, and I'll be back soon with another weekend project or another restoration. Good night.